Hey, this is Mr. Ray, and this is Physics Honors, and we're going to be doing the photoelectric effect. And now, I know you might say, we just did the photoelectric effect in the last video. Well, we're going to do the photoelectric effect and take a look at the actual experiment with calculations. And so, if you take a look right here, the experiment that we went through before, remember that we had a piece of metal and we were shooting with a photon of light, and that photon of light had enough energy that the metal absorbed some of that energy and the electrons came off with more kinetic energy, which meant they were moving. Okay, and so as we take a look at what's happening here is on one side of the equation, and this is the easiest way I think to do it, is one side of the equation we're going to be taking a look at the photons of the light, or the wave-like behavior of light. And the other side, we're going to take a look at the electrons, or the photoelectrons, and that's the particle-like behavior. Okay, and I'm going to keep this different with red and blue in terms of my equations. I'll give you all the equations. We'll go through a problem here, and we'll take a look at each one of these things. Now, with photons or waves, the equations we're going to use is the speed of light equals wavelength times frequency. Okay, and the speed of light is always 3 times 10 to the 8th meters per second. That's equal to the wavelength times the frequency. We also have the equation energy equals Planck's constant times frequency. And Planck's constant, this h value, is either going to be 6.63 times 10 to the negative 31st joules seconds, or it's going to be 4.14 times 10 to the negative 15 electron volts seconds. Now you might say, which h do I use? Do I use 6.63 times 10 to the negative 31st? Do I use 4.14 times 10 to the negative 15th? Well, if you want your energy to be in joules, you're going to use the first one. Okay? If you want your energy to be in electron volts, you're going to use the second one. And you might say, well, what's the equivalence between electron volts and joules? Is 1 electron volt is 1.6 times 10 to the negative 19th joules. Okay? Now, we're going to be doing a lot of our problems in electron volts, believe it or not. So you're going to be using this 4.14 times 10 to the negative 15th a lot. But we will use joules sometimes, and you'll see even in the problem today we'll use joules. Now just keep in mind we can actually combine these equations into one, which is energy equals h times c, that's Planck's constant times the speed of light, over the wavelength. So if you're being given the wavelength and you want a shortcut to find the energy, just use this equation. It kind of combines both of those together. Now over here you can see the metal absorbs some. Okay, so the metal absorbed, how much did the metal absorb? We called that the work function. Okay, the work function. And that is this funky looking symbol right here called the work function. That's how much it's going to absorb. Now the energy that's going to be released is the maximum kinetic energy. And we have an equation for the maximum kinetic energy. The maximum kinetic energy is going to be 1/2 mv squared. If you remember back at our kinetic energy units in the first semester, this was our equation for the kinetic energy of a particle. Okay. Now, what do we use for the mass? Well, we're using electrons. So the mass of an electron is 9.11 times 10 to the negative 31st kilograms. And so these are the equations I'm going to use. I'm going to use these equations. C equals wavelength times frequency, E equals Planck's constant times frequency. For photons or waves, in the particles, we're going to use this equation of the kinetic energy max equals 1/2 mv squared. And there's an equation that relates both of these, which is called the photoelectric effect equation. And it says this: the kinetic energy maximum equals hf, that's the photon energy, okay, hf, minus the work function, and you can see right here the kinetic energy max relates that guy. The hf is the energy of the photons, and the work function is how much the metal absorbed. Okay, now this equation, and I'm going to write it out again, kinetic energy max equals HF minus the work function. I'm hoping that you can see this is in a y equals mx plus b format. It is in a linear format. And so if I kind of take this step by step right here, you can see the kinetic energy max, the kinetic energy is on your y-axis. The frequency is on your x-axis, isn't it? Okay, and that relates with y equals mx right there. You can see the slope right here. The slope, this m, the slope is going to be Planck's constant. So the slope is equal to Planck's constant of this line. Okay, it's going to be equal to 4.14 times 10 to the negative 15th if we're doing electron volts and the frequency in per seconds. You can see right here the y-intercept is going to be the work function, but it's going to be on the negative value. So the y-intercept is negative of your work function. So that's how you find your work function right there. And you can see right here is your, I'm going to put this in maybe gray right here. This right here is called the threshold frequency. The threshold frequency. Why do we call it the threshold frequency? This is when the kinetic energy is equal to 0, isn't it? This is where the y value, the kinetic energy, is equal to 0. And so if it's equal to 0, that means your HF is equal to your work function. Okay? And so as we take a look, this gives you the equation, kinetic energy max equals HF minus the work function. Now, let me kind of show you what's kind of going on in here. Here I have some waves of light, and so the waves of light start hitting my work function, and so it absorbs, and then right here, this threshold, that's where if the energy is any greater than this, that means it's going to eject electrons off, and because the energy is greater. This is the energy that the metal absorbed, and then you can see all the leftover energy. The leftover energy was the kinetic energy max that the electrons will have, the energy. Okay? So let's go through a problem. So here I have a photoelectric effect problem. And so I'm going to do my photons, which means speed of light equals wavelength times frequency. 3 times 10 to the 8th meters per second equals the wavelength. The wavelength is 400 nanometers, or 400 times 10 to the negative 9th meters. So we change nanometers into meters because we need to be in SI units. 400 times 10 to the negative 9 meters, which means I can just divide to find my frequency. So try this in your calculator along with me. The frequency of this light right here is going to be 7.5 times 10 to the 14th hertz, or per seconds. So now I can find my energy. Energy equals Planck's constant times frequency. Okay, so let's say I'm going to use the 4.14 times 10 to the negative 15 electron volts seconds, and I multiply by the frequency of 7.5 times 10 to the 14th hertz. I end up getting a energy of 3.1 electron volts. So that's how much energy this light has. It is 3.1 electron volts of energy. Now let's say I use the 6.63 times 10 to the negative 34th joules seconds, and I multiply that by 7.5 times 10 to the 14th hertz. Well, that's going to just give me the same energy, but the energy is going to be in joules. So I end up getting 5 times 10 to the negative 19th joules. So this guy has this 400 nanometers of light, okay, has 3.1 electron volts, or you could say 5 times 10 to the negative 19 joules. I hope you can see why we do electron volts, because 3.1 is an easier number to use than 5 times 10 to the negative 19th. Okay, so that's why we use electron volts. It's just easier. Now, do you see how some of this metal absorbs some of this? And what did they say? They told us that the maximum kinetic energy is 1.1 times 10 to the negative 19th. So the electrons off came 1.1 times 10 to the negative 19th joules. Now think of that. about that. Think if, and I'm going to use a model right here, think if you had $5, and at the end of the day, you had $1.1 coming off, $1.10. That means someone must have absorbed some of your money. And I hope that makes logical sense. So you can say kinetic energy max equals HF minus the work function. What's my maximum kinetic energy? 1.1 times 10 to the negative 19 joules. And that equals my, remember this number is my waves, so 5 times 10 to the negative 19th joules minus my work function, which means my work function, which is how much energy the metal absorbed, well, that was 3.9 times 10 to the negative 19 joules. Think about that logically. You had $5, someone absorbed $3.9, which meant you had $1.1 left over. Okay, that makes logical sense, hopefully. So the work function, or the metal, 3.9 times 10 to negative 19 joules. Okay, and off comes 1.1. Now, that 1.1 times 10 to negative 19th negative 19 joules is the kinetic energy of the particles, the electrons. Okay, so you know kinetic energy max equals 1/2 mv squared. You know your kinetic energy is 1.1 times 10 to the negative 19th joules. 1/2, we have 9.11 times 10 to the negative 31st kilograms v squared, and you can do some algebra here. You can multiply by 2, divide by 9.11 times 10 to the negative 31st, and then square root to find the velocity. And the velocity of our electrons coming off ends up being 4.9 times 10 to the 5th meters per second. And ask yourself, is that a good number for an electron, the speed of an electron? Heck yeah, because it's less than the speed of light. It can't be greater than the speed of light. And so you can see how we started with our photons. We use our photon equations to find our energy. Once we knew our energy, we could find our work function if we needed. And so then we knew that the maximum kinetic energy was 1.1 times 10 to the negative 19 joules, and we were able to find out the velocity of our electron. So that was the photoelectric effect, and those are our calculations. So make sure you practice these equations, and we'll get some practice tomorrow. Make sure you do your self-assessment. Photoelectric effect, Mr. Aiden signing off. See you guys.